I'm often asked if MMC can be used with profile. The answer is sort of. You are not allowed to ever apply MMC to the profile tolerance. You are, however, allowed to modify datum features referenced in the profile tolerance, provided they are features of size. Here, datum features B and C have been modified at MMC. This doesn't change the profile tolerance zone, which is still 0.4. It does allow the profile tolerance to float a bit when the datum features are made larger than their virtual condition. Let's say this part is to be inspected using an overlay on an optical comparator. If datum features B and C had been applied RFS, the part shadow could not move or float on the datum simulators. Since datum features B and C are modified at MMC, the overlay includes the virtual conditions of the datum features, shown here in red. An inspector could float the outline of the part around to bring it into the profile zone of 0.4, provided the datum features did not violate their virtual conditions. Be sure to download the hard copy of this tip so that you can study it further. And I'll see you next month. A common error on a drawing is to apply only angularity to features and believe the location is controlled. Position locates features of size. Profile of a surface is the only geometric tolerance that locates surfaces. The orientation tolerances of perpendicularity, parallelism, and angularity never locate features. The angled surfaces on this part, for instance, need to be located relative to the datum reference frame. If angularity had been applied, the drawing would be incomplete. Profile of a surface locates the surfaces in addition to controlling the angularity. The angled surfaces of the V block cannot be tipped more than the profile of a surface tolerance of 0.1. If the orientation of these surfaces needs to be better than the orientation provided by profile of a surface, an angularity tolerance may be added as a refinement. Locate first, then refine for orientation second, but only if necessary. Here the angularity tolerances float independently within the profile of a surface tolerance. Since angularity does not locate, the angularity tolerances float separate from one another. In order to have them float as a pattern, a composite profile tolerance should be used rather than angularity. But that's another tip for another month. Remember, you can look up over 100 My Tips by selecting the topic from the tip index. And I'll see you next month. This is a problem that just won't go away. Here is another case where angularity cannot fully define the feature. The original drawing had angularity rather than the position tolerance applied to the 10 millimeter wide slot. The drawing shows that the center of the slot should be in line with the datum axis. Angularity would assure that the slot is at the 60-degree basic angle, but ignore that the slot center is supposed to pass through datum axis B. To keep the slot in line with datum axis, position needs to be applied to the slot's size dimension. If the angle of the slot needs to be controlled better than the angularity provided by the position tolerance, an angularity tolerance may be added as a refinement. As we teach in our GD&T seminars, for features of size, locate first with position and refine with orientation, but only if necessary. I'll see you next month. There continues to be the misconception that if a feature is labeled as a datum feature, its use is somehow implied. Take the drawing shown. The position tolerance on the hole references datum features A and B, but not C. Therefore, the hole must be perpendicular to the plane established by datum feature A and 20 millimeters from the axis established by datum feature B. Datum feature C has nothing to do with the position of the hole. Yes, the hole is shown on the center line that is perpendicular to datum feature C, so we know what the goal is. But since the datum feature C was not referenced in the position tolerance, there is no limit to how far the hole can be off the 90-degree angle. In order to avoid this, all you have to do is add datum feature C to the position tolerance. See you next month. It is important to recognize the features of size on a drawing. These are the features that rule number 1 applies to. In addition, when certain geometric tolerances are applied to a feature of size, the control is on the feature's center point, axis, or center plane. Here's a handy tip for those struggling with identifying features of size. I call it the caliper rule. Tolerance dimensions that you would be tempted to measure using this end of the caliper are features of size. You use this end of the caliper for the features that contain opposed points. If you find that you would use the probe to measure a tolerance dimension, there must not be opposed points, so the dimension is not a size dimension. The depth of a hole, for instance, is not a size dimension according to the standard. So if you think the depth of a hole is a size dimension, get over it. Be sure to download this tip to read why identifying features of size can really help with understanding GD&T. See you next month. Here's a little test that one of our faithful readers asked me to create. He tells me that 9 out of 10 folks at his work get it wrong. Given the drawing, does figure A or B more correctly illustrate the datum reference frame, which establishes the origin of measurement for the profile tolerance and the position callout on the 2 holes? If you said figure B, you are correct. The dimensioning may have thrown you off. You cannot go by the placement of dimensions like we used to in the old plus-minus days. You have to follow the datum precedence stated in the feature control frame. Because the large hole, datum feature C, is the 3rd datum referenced, it can only establish the measurement origin from left to right. The up-down origin is established by datum feature B, which is secondary. Since the dimensions are basic, they may be placed on the drawing any number of ways without changing the meaning. In fact, with the new ASME Y1441 standard, dimensions often may not even appear on the drawing. See you next month. This month's tip is parts do not have center lines, features have axes. You know, it's hard for me to believe that some companies continue to work to in-house standards that refer to the part center line. And I continue to see the datum feature symbol placed on center lines on a drawing. The standard allows this only if datum targets are used to indicate the datum feature. That was not the case for a company designing lens systems to be used in space. Here's a simplified redraw of one of their lens barrels. They applied a total runout to a critical diameter that would interface with a lens. This means that when checked with an indicator, the full indicator movement could not be greater than 6/10,000ths when the part is rotated about datum axis A. The customer placed the datum feature symbol on the center line. The supplier used a convenient feature, such as the largest OD, to check the runout. Unfortunately, the customer held it the way it would assemble in the lens mount, and the parts failed. The resulting lawsuit cost the customer nearly $8 million. The problem is that each cylindrical feature of a part has a different axis. Holding the part differently gives different results. Heck, if parts could be made perfect, there would be no need for tolerances on drawings. So we must make it clear on a drawing which features to use to establish a datum. This way, the drawing makes clear the design intent. This problem is easily avoided by following the standard. The datum feature symbol must identify a feature to use to establish a datum. Here, by associating the datum feature symbol with the size dimension, everyone knows what the drawing means. The supplier knows how the part will be inspected and has a better chance of making the parts right the first time. Or your company can live by that old adage that engineers don't make mistakes. They make revisions. This one could have been avoided. I'll see you next month. Don't be surprised if you don't find your parts in the Y14.5 standard. The standard is a collection of building blocks. There are an infinite number of ways to combine these building blocks to control your parts and still be in compliance with the standard. The standard does not, for example, specifically show how to tolerate such parts as preformed hoses, tubes, and bent rods. However, the building blocks for controlling this sort of part are found in the standard. Here's a drawing of a preformed tube. Datum feature A is the cylinder at the end of the tube, and it establishes an axis. That axis is the intersection of two perpendicular datum planes. Datum feature B is a cylinder at the other end of the tube, and it's used to orient the datum planes. Datum feature C is a face here at the end of the tube, and it gives us our third datum plane. Together, these three planes establish your origins of measurement. The rest of the tube is controlled by the position tolerance applied to each element between points S and T. Each element or slice must be within 0.8 millimeters of its basic location if it's made at its largest size or maximum material condition. Together, these slices define a boundary that the surface of the tube may not go outside of. If you need to control your formed tubes, rods, and other similar shapes, be sure to download this tip and study it further. And I'll see you next month. Controlling slots and other irregular shapes has always been a challenge. The standard gives us two ways to tolerance slots. The first works for slots only. The length and width of the slot are toleranced as two features of size. A position tolerance with the word boundary is applied to each position tolerance. The size limits are controlling the size and form of the slot, although what is actually allowed on the radii is a little fuzzy. The position tolerance controls the location and orientation of the slots to the datum reference frame. The other method will work for any internal or external shape, including slots. A profile tolerance controls the size and form of the slot all around. One position tolerance controls the location and orientation of the slots to the datum reference frame. In this case, there is an inner boundary that the slot may not violate. The slot can move left, right, up or down, and even tip, as long as it doesn't come inside this boundary, which is probably the space needed by the mating part. I like the approach that will work for all irregular shapes. Remember to download and print out the hard copy of this tip and other tips on our site. And I'll see you next month. This month's tip is don't forget simultaneous requirements. The standard tells us that when features and patterns of features have the same datum reference, they are considered to be a pattern. This rule is not well understood, but it is a rule. If we take a look at this drawing, we have three datum features called out. A is the surface, B is the hole, that establishes an axis, and C, the width, stops rotation about that axis. If we were to design a gauge for that part, these would be the values for the gauge. If you download this tip and calculate the virtual conditions, I think you'll find that these numbers are correct. If, however, we were to take a look at another drawing that does exactly the same control, here we only have one datum being referenced, but all of the features are referenced to that datum. Because of the rule of simultaneous requirements, then, all of these features are a single pattern, and they must meet their tolerances simultaneously. So, the very same gauge we saw for the first drawing would work for this one. They're identical. Simultaneous requirements works well when you're checking a part using an overlay and an optical comparator, or, as we saw, a hard gauge. However, if you're trying to check a part like this with a coordinate measure machine or layout inspection, you'll find simultaneous requirements can be very difficult to inspect. Since the design intent didn't change, and both drawings have the same meaning, the person making the drawing should definitely take into consideration how the part will be inspected. And I'll see you next month. This video was created to illustrate the speaker notes and the animations that you'll find in the PowerPoint presentation. As I go through these next slides, I will be reading from the handouts. Point out that this chapter deals with locating features of size. Use the GD&T hierarchy pyramid to introduce the chapter by saying, once datum features have been identified and controlled, you have to locate the other features. We now know that any surface may be located using profile of a surface. We also know there's a special group of features known as features of size. The size and form of these features is controlled by the limits of size in accordance with rule number 1. If the feature of size is a cylinder and is coaxial to a datum axis, we will see in the next chapter that there are several ways to control the location. This chapter shows how to locate these features of size using the position tolerance. Just to be certain that no one thinks you are fostering violence in the workplace, mention that shooting is an Olympic sport that is socially acceptable. Then challenge someone to a shooting contest. Explain that the goal is to hit where the two lines intersect. The first shot you will explain is your shot, and the second shot is their shot. Then ask them who won the contest. Using a string or pointer, illustrate that your shot is further away. When the posted sign appears, explain that if they're using plus-minus tolerances, your shot would be good where theirs would be bad. For instance, if they were using plus or minus 5 thousandths on a drawing, this shot is further away than 5 thousandths. And even though your shot could be as much as 7 thousandths away, it would fall inside the plus-minus 5 thousandths tolerance zone. Then explain that the position tolerance gives you a cylindrical zone, and there is a 57% increase in tolerance. And if they use the MMC or LMC modifier, you get even more tolerance. Ask which features on this part are features of size. Explain why Datum Feature B does not need a position tolerance, since it is establishing an origin. Remind them that the radius may or may not have opposed points, and therefore is not a very good feature of size. As the arrow moves around the slide, ask them to answer the question: is the arrow pointing to a size dimension? When you first click on the mouse, Bean will appear shrugging his shoulders. Of course, the first one is pointing to a basic 45-degree angle, which would not be a size dimension. The 5 plus or minus 0.1 is the size of the hole, so this would be a feature of size and require position. The 100 picks up its general tolerance of plus or minus 0.2 from the general note, and this is a feature of size, once again requiring position. The same is true for the 50 diameter. The 40 is a basic diameter, just locating the 5 millimeter hole, and it is not a feature of size, nor is the 76 diameter. The 12 diameter is the size of the two holes, and a position tolerance would be required. The 40 is a basic dimension locating the surface which is at the bottom of the key seat, and that surface would have to be located using profile. So the 40 is not a size dimension. The 14.1 to 14 is the width of a feature of size, the width of the key seat, and it would require a position tolerance to keep the center plane of the key seat in line with the datum axis. The 30 is Datum Feature B, and this establishes the origin of measurement. So even though B is a feature of size, it does not require position, and its relationship to the primary datum feature would be perpendicularity. You might point out that had position been used on Datum Feature B, the result would be the same. Explain that the 60 millimeter diameter feature would be able to trap a gauge pin or equivalent and to establish a reproducible center. Therefore, position may be used to locate this feature. Discuss the two position tolerances. Point out that when maximum material condition or least material condition is applied, there are two ways to look at the tolerance. One way, The traditional way is to think about the tolerance zone controlling the axis or center plane of the feature. Discuss the calculation of virtual condition for each of the features. Use the dynamic tolerancing diagrams that were introduced in previous chapters to help with this. Point out that the virtual condition is a boundary that may not be violated. Because of this, it is often possible to evaluate position when the tolerance is modified at MMC by using a hard gauge, which assures that the virtual condition is not violated. Explain that these position tolerances may be thought of as single limit controls, meaning that there is a single boundary that the surface of the feature may not violate. This boundary is called the virtual condition. This concludes the video which demonstrates the speaker notes and animations found in the PowerPoint. Datum features must be of sufficient size. Datum selection is one of the most significant aspects of applying GD&T. In section 4.3 of the standard, it says that a datum feature should be of sufficient size to permit its use. Well, the major use of datum features is to arrest or take away the degrees of freedom or movement of a part so that it can be reproducibly inspected. On this drawing, the primary datum feature is this large hole in the middle. Now this is a thin part. We're asking this cylindrical feature that's not very long to take away 4 degrees of freedom. That's ridiculous. This hole isn't long enough. That would be like trying to reproducibly grab this disc by the diameter. You just can't do it. If you do this on a drawing, please do not tell anyone that you've been reading my tips. Now the second drawing has a large flat surface as a primary datum feature. It can arrest 3 degrees of freedom. The center hole then is your secondary datum feature, and now it only has to take away 2 degrees of freedom, which it can reproducibly do. The datum features you pick have to be usable. By selecting practical datum features, your designs will perform better, and you can let everyone know that you are a faithful reader of my tips. I'll see you next month. Simultaneous requirements, again, because I keep getting questions about this. Let's say we have a shaft with a key seat on one end and a pair of flats on the other. The question is, how well do they have to be oriented to each other? On the drawing, they're shown at 90 degrees, so we know what the goal is. But what's controlling their perpendicularity to one another? Well, let's take a look at the drawing. The large diameter is called out as datum feature A because it rides in a bearing. And then the flats and the key seat each have a position tolerance relative to the datum axis. But there's no mention of their relationship to each other. Let's say I have a V-pulley on one end and a friction disc on the other. I really wouldn't care about the relationship. But if I had a timing gear on one end and a cam on the other, I would care a great deal. Well, since they have the same datum reference according to the simultaneous requirements rule, they have to also be perpendicular to one another within their tolerance zones. If you do not want to require this relationship, you have to add the abbreviation separate requirements, or SEPREQT, under each of the position tolerances. Doing this will help keep the cost down. So if you do not care about cost, don't bother. Hey, be sure to visit our website to download this and over 100 other tips, and I'll see you next month, unless you're out looking for a new job. Thanks for all the great tip suggestions you sent in. And here's a tip that resulted from many of your emails. A lot of people continue to be confused over what can be applied on a drawing and what has to be stated. So I thought this month's tip could cover some of the things that are implied on a drawing. Dimension-wise, there are several things that can be implied. When you see lines at 90 degrees to one another or right angles, there's an implied 90-degree angle, whether it's center lines or lines representing features on the part.
This is also true for lines that are shown parallel. There's an implied 0-degree relationship between the lines. Also, when features are shown on the same center line on the drawing, it's implied that the goal is that these features be coaxial. And the same is true for symmetrical. And if I have a line tangent to a circle, I don't have to say anything about it on the drawing. It's implied to be tangent. And the list goes on. So there are many things dimension-wise that are implied, so we don't have to put a lot of extra dimensions and notes on the drawing. What about tolerances, though? Well, the standard says tolerances must be stated. I know. You'd rather not have to put all those tolerances on the drawing. You say you want them to be implied, too. Well, I want a pony. But let's face it, that's not going to happen. So when we look at the standard, it says, although there's a lot of dimensions that can be implied, tolerances must be stated on the drawing.
Steve Eccles, a principal design engineer for Honeywell's Turbo Machinery Systems division, suggested the topic for this month's tip. Steve and I are both irritated by the people who think the primary datum feature for a hole has to be the surface that is perpendicular to the hole.
Let's take the support bracket as an example. It mounts onto this base plate, and its main purpose in life is to locate and orient the pivot pin. Functionally, this back surface would want to be your primary datum feature, and so I've labeled that as datum feature A. The part is located using these two bosses, and so those two bosses have been made datum feature B. Then the hole that is going to receive the pin is held in position to AB. This position tolerance is not only locating the hole relative to A at that 25 millimeter dimension, but it is also controlling the parallelism of the hole relative to the primary datum feature. Some people might think that this surface or the one on the other side should be selected as the primary datum feature for the position of this hole, because they may think that that's how this is going to be supported when the hole is put in the part. But that would be silly. That's not how this part works. A few things to keep in mind when a designer or design engineer selects datum features based on how they think the part will be produced. First of all, they are usually guessing and really don't know how the part is going to be made. But even if they do, the part may not function that way, so you get a part that's easy to produce, but it doesn't work. And what if the process changes or you change suppliers? Do you really think anybody's going to go back and change the datum referencing on the drawing? No way. The function remains the same, even if the process changes. So let's select datums based on their function.
This month's tip is entitled Apply Profile of a Surface to Surfaces. It really does matter where you place a geometric tolerance. Often it can change the meaning of the drawing. Other times it's just plain wrong. Profile of a surface is frequently applied incorrectly. This profile of a surface, it applies to surfaces. It must be applied to the surface on the drawing. On this drawing, you see that there are two places where I've put it where it's incorrect. It's associated with dimensions. You can't do that. The one that says OK applies to a surface. If you're having difficulty applying your geometric tolerances, give us a call. And I'll see you next month. Mike Wright, a senior quality engineer for Atom Aircraft, suggested the topic for this month's tip.
Here's a tip that should sharpen your geometric tolerancing skills. The title is Add a Note to Expand a Pattern for Composite Tolerancing. On this plate, I would like to control these three holes as a pattern. The connector pilots on the larger diameter, and then the two smaller holes are for fasteners. Your first task would be to set up your main datum reference frame. I've picked A as the primary datum feature, which is this face. B is the width, which gives me a center plane down through the part. And C, the length, which gives me another center plane. and I've applied geometric controls to those datum features. Now the question is, how do I control these three holes? What a lot of people will do is identify the larger hole as a datum feature, position it on the part, and then to get a good fit, we'll probably have to refine with a perpendicularity to a tighter tolerance relative to A. Then position the two holes relative to A, D, B. Now this requires a new setup, and it also required that additional geometric tolerance of perpendicularity to make certain that the two smaller holes follow the larger hole around on the part. And this is technically correct. Another approach, though, would be to use composite tolerancing. A lot of people think that if the holes are of different sizes, you can't use composite tolerancing, but that's not true. If you refer to section 511.16 of the Y14.5 standard, 1994 edition, you'll find this approach. Now this says that the three holes have to be somewhere on the part, in other words, positioned within 0.4 to my main datum reference frame, and then a tighter position with respect to one another to guarantee the fit that I would like. This approach eliminates one setup, that auxiliary datum D, and I don't need that refinement of perpendicularity.
Keeping features in line requires a geometric tolerancing. Showing features in line isn't enough to make sure that they'll be made that way. On this drawing we have three surfaces. I have extension lines between them, but that doesn't guarantee that they're going to be lined up. I have to apply a geometric tolerance, as I have here with the profile, and say three surfaces to make sure that they won't end up looking like the part I'm showing up here. On this next drawing, I have three separate cylinders. They all have the same size, but if I didn't have that position tolerance there, I could end up with a part that looks like this. So, we need to make sure that we apply geometric tolerances when we want features to be coplanar or coaxial. In other words, lined up. And I'll see you next month. One more time. It's the datum, not the datum feature. I must get a question on this at least once a month. This time the question was, how can the datum be bowed and have a parallelism on a planar surface relative to it? Well, it can't. Before I show you the drawing, let me say that I didn't use good practice on the drawing, but I wanted to make a point. On this drawing, I put a flatness of 0.5 millimeters, and then that becomes datum feature A. Then I have a parallelism within 0.1 to the plane established by A. So one way to check this would be to put the part down on the surface plate and run an indicator parallel to the plate. So you can see here that the datum feature itself could be bowed, but I'm hitting the high points or extremities. The datum simulator itself should be a very good plane, and the indicator is running parallel to it. Therefore, the parallelism could be within the 0.1, even though the datum feature itself could be out by as much as 0.5. I hope this cleared it up, and I'll see you next month. I'm often asked how to set up a part when a datum feature is unstable. In other words, how do you deal with a datum feature that is a rocker? If we take a look at this drawing, we see that datum feature A has a flatness on it. Now it could be concave or convex. If the surface is convex and I place it down on the surface plate to inspect the part, it might rock around a bit. This is showing you that there are several different datum planes that I could possibly use. In fact, if I set it down and it does rock, there's an infinite number of planes. So which one do I use? Well, if we look at the Y14.5 standard, it says you pick the optimum one. The math standard, Y14.5.1, clears things up a little bit. It says, yes, there is an infinite number of planes there. They're called the candidate datum set. And you are allowed as an inspector to pick the one that will bring the part into tolerance. Please don't forget simultaneous requirements. Notice here that the profile is to A, B at M, C at M, and the position is to A, B at M, C at M. So there are an infinite number of datum planes if this is a rocker, but you have to pick the right one that will bring all the features into their tolerance zones simultaneously. There's other ways, of course, to deal with this. Datum targets, restraint nodes, tighter flatness controls. We've covered those and other tips. I'll see you next month. A lot of people remain confused over the differences between composite and two single segments. So to help clear it up, I created a drawing. On this drawing, I have a pattern of two holes. And I've shown 4 possible geometric controls. The first 3 are composite. Notice there's only one position symbol. The last one is 2 single segments. In all 4 cases, the upper segment is locating the 2 holes within 0.4 relative to the datum reference frame. Let's take a look at how the lower segment changes the meaning of the drawing.
The first composite tolerance does not have a datum reference in the lower segment, so it is only controlling the relationship of the holes to each other. By bringing down datum feature A, the perpendicularity of the 2 holes would be tightened up to within 0.1. So the holes can still move around as a pattern relative to datum planes established by B and C, but they have to remain perpendicular. So that means the pattern could even rock, as you're seeing here. By bringing down datum feature B, though, we can stop this rocking. So the pattern must be now within 0.1 to each other, perpendicular to A, and the orientation of the pattern cannot be off by more than 0.1. They can still move around 0.4, however. The last feature control frame is called 2 single segments. Notice there are 2 position tolerances. This is controlling the location between the holes, the perpendicularity to A, and the location to B within 0.1. The pattern can float relative to the plane established by C within 0.4.
I hope this cleared it up for all of you, and I'll see you next month. Now let me show you some of the samples of our materials.
Like I said, we use the GD&T hierarchy. In fact, that's the title of our textbook. We use several different techniques, including flowcharts, and here's a little animation to illustrate the hierarchy. We point out that the geometric controls are tools in your toolbox. But like any tools, if you don't know how to use them, they're not going to do you any good. So we tell people what to go for first. Once they've established their origins of measurement by using datum features to establish their datum reference frame, then you open up the toolbox and we find that location is on top. You must locate other features relative to these origins of measurement. And then, only if necessary, might you go further into the toolbox to pull out the orientation tolerances. You got them for free with location, so the only reason to get the actual orientation tolerances is to tweak what you already have controlled. And once in a while, you have to dig way down into the toolbox for the form controls, and yeah, we put profile of a line down there. Because we get form control for free with size tolerances, many times with locating tolerances like profile, and with the orientation tolerances on surfaces. So it's rare that you need to dig way down into the toolbox. This is just one example of the analogies that we use to make GD&T clear. You'll notice down at the lower right corner of the slide is the page number that this would relate to. It makes it easier for the folks to follow. Throughout our training materials and our PowerPoint, we use real application. This is an example of a fuel valve. It's a real fuel valve. And we show the importance of selecting your datum features in an order that reduces the number of tolerances in your assembly. And here's an example of a tolerance analysis that we illustrate. Included with the PowerPoint are speaker notes so that you know what we think ought to be said with each one of the slides. Of course, you can customize that all you want. As I said, we use several case studies,
Here's one of a roller bearing. This was a brand new roller bearing as shipped. These two rollers were right next to one another. And we show how Rule 1, if used correctly, would have picked this problem up, so it wouldn't have been shipped to the customer. This is an overlay that the students have that they get to work with, and first we calibrate our ring gauge at 20 millimeters and our anvil mic and our 2-point micrometer. We then bring in that 5-lobe part, which is very common in centerless grinding, 5 and 7-lobe parts, even 3. And we show how, no matter how you mic that bearing, you could not detect the lobing effect. And even if you put it in the anvil mic or tri-mic, as you rotate it, the mic would not change. But if they had followed Rule 1 and checked the perfect form at the maximum material condition, they would have found that that had a lobing problem. So a lot of use of color in 3D. We stick to the terms that are found in the Y14.5 standard. We're sticklers about having the terms used properly. We use a lot of analogies and animations to explain things like the 6 degrees of freedom. We point out that an airplane in space, as with all parts, has 6 degrees of freedom. The 3 tudes, latitude, longitude, and altitude. And the other 3 tudes, which are the attitudes of pitch, roll, and yaw. And how we use datum features on parts to constrain some or all of these degrees of freedom. So then we walk through the various features on the part, and we show what degrees of freedom remain. In this case, if I set this flat surface down on a surface plate, I still can translate in 2 directions and rotate. So I must have taken away the other 3 degrees of freedom, which would be 2 rotations and 1 translation. We like to, whenever possible, show examples of real inspection equipment, this being a surface plate. After we've introduced the concept, then we ask questions. Many of these questions are found in our workbook, as this one is, and we've supplemented with additional questions that are not found in the workbook. Because our PowerPoints can be customized, you have the option of skipping these if you have a very short amount of time to cover the work. We emphasize design intent, which is what the standards emphasize, and we show how by walking through assemblies and looking at the features that constrain the degrees of freedom, you can find the most efficient way to select your datum features. And then we show the resulting datum reference frame. Where a concept is a little tougher to understand, we make use of video. Here we're explaining how the datum shift that you can get when a max material boundary symbol is applied to a datum reference isn't really giving you a bonus, it's giving you a shift. In this case, you would get datum shift left-right, but not up-down. And to illustrate this, we used a hard gauge and a video. And we show how the gauge pin won't fit through this hole. Once we shift the part around on the gauge, there's the datum shift in that one direction, then we can get the part to be accepted by the gauge. We're not pushing gauging, but sometimes we use gauges to illustrate a concept. It's easier to visualize that way. Another difficult concept for folks to grasp sometimes is simultaneous requirements, so we use animation to illustrate controlling the relationship between this key seat and the pair of flats on the other end of the shaft. For some design requirements, where I have a cam, for instance, on one end of the shaft and a timing gear on the other, I want simultaneous requirements, which is the default of the standard. Since these features reference datum feature A, they become a pattern. Simultaneous requirements. And if I don't want that pattern, I must say separate requirements. In this application, now a friction disc is going onto the pair of flats, and a V-pulley is making use of the key seat. So here I really don't worry about the orientation, and I would say separate requirements. So a part like this would be acceptable. Here's a couple more examples where we're using real parts to illustrate a concept. This is the one for customized datum reference frameworks, which is difficult for people to grasp. Here's another example with a tool holder and how customizing degrees of freedom allows us to change where the origin is from out here at the vertex of the cone to this surface, which is much easier to find. Using 3D and color really makes it easy to explain things like the various tolerance zones. So we illustrate all of the tolerance zones in 3D. We also illustrate sample verification. And in this case, talking about position, we use the color in 3D to explain the difference between the surface interpretation and the axis or center plane interpretation. Here's a dynamic tolerancing diagram where we put size along the x-axis and the geometric control along the y, and point out that this position tolerance applies at the smallest hole, which would be at 11.8. And as that hole gets bigger, you get additional tolerance because of the maximum material condition modifier. We feel that these dynamic tolerancing diagrams really help the learner to grasp the concept of max material and least material condition. And to point out that there is a boundary that is being protected by this position callout. It's known as the virtual condition boundary, or the inner boundary, or more recently the max material boundary. If we were to build a hard gauge, then we would build the hard gauge at that 11.5, adjusting for gauge tolerance and wear allowance, of course. And so a hard gauge with sliding pins and a sliding block might look something like this, where we first establish our datum reference frame and then verify that the boundaries haven't been violated by the part. And then here's one of the examples of an exercise that the students need to work on to create their own dynamic tolerancing diagram. And they have the opportunity to calculate gauge sizes. This animation shows how concentricity and circularity or cylindricity are both controlled by the two runouts. All of the animations that you've seen in this presentation are exactly as they appear when you run the PowerPoint slides. There continues to be this huge controversy over how to orient datum planes. This tip should put that controversy to rest. The title of the tip is Orienting Datum Planes. On this drawing, we have a position tolerance on the 8mm hole. The primary datum feature, A, is regardless of feature size, and it's this 15mm hole. So this means I would fill it with the largest inscribed cylinder, and the axis of that cylinder would be my primary datum, and that would be the intersection of two mutually perpendicular planes. My secondary datum feature, B, is also regardless of feature size, and it's this slot. Let's just see how I use that slot to orient these datum planes.
As I mentioned, first you would fill datum feature A with the largest inscribed cylinder. This gives you an axis. The axis is the intersection of two mutually perpendicular planes. The question is, how do I now orient these datum planes? Well, the slot was picked as a secondary datum feature. There's two ways that I can use this to orient the planes. One way is to locate the center plane of parallel planes at the 14 basic dimensions seen on the drawing. Then have those planes expand to fill the slot, as you see here. The second way would be to fill the slot and then rotate to orient the datum planes parallel to the center plane of the slot. This one is preferred by a lot of coordinate measuring machine operators. The correct answer? Locate parallel planes at the basic location and expand them to fill the slot, because datum simulators are perfect in form, orientation, and location.
I hope this put the controversy to rest, and I'll see you next month. A lot of you have asked why I don't have more tips on perpendicularity, or any of the orientation tolerances for that matter. Well, the reason is there isn't a whole lot to say. If we take a look at this drawing, yeah, I have perpendicularity on a secondary datum feature because that's its relationship back to the primary. But beyond that, I don't need perpendicularity usually because I get it for free. I get it for free with position, with the profile tolerances, and with the runout tolerances. And the other orientation tolerances also. Here with profile, I'm getting angularity for free. So since we get them for free, I don't need them usually unless it's a refinement. So when do you use perpendicularity? To control a secondary or tertiary datum feature to a higher precedent datum because that's often its relationship. Or to control perpendicularity better than that control provided by the location tolerances. Start with location, then refine with orientation, and then the form controls. But only if necessary. And I'll see you next month.
Okay, here's the deal. You have a shaft, a hole, a slot, or other feature of size that is interrupted by another feature such as a groove. Now, is it still one feature or has it become two separate features? And what if there are multiple grooves? Now what do? Well, you must tie them together somehow. So, this month's tip is tie those interrupted features of size together. On this part, we have two features that have the same diameter, and once upon a time this was a continuous shaft, but a groove has been cut between these two diameters, so it doesn't matter what it was originally. There are now two individual features. Because when this goes in its assembly, these two features take away the most degrees of freedom, they want to be our primary datum feature. I need to tie them together to keep them in line. One way is to use position. Now, in the past, this has been a problem because the standard in the 1994 revision said that with position you had to have a datum reference. Even though when we looked in the composite section of the standard, we saw support for having position tolerance without a datum reference in a second segment of a composite. In any case, in the 2009 revision, this is allowed where we have features of size that I'm going to use as a primary datum feature, and I need to control them with respect to each other. Because I'm using zero at maximum material condition, there is a boundary at perfect form, the virtual size, in other words, at 16.02. The 2009 revision gives us another way to accomplish the same task. We now have this symbol called the continuous feature symbol, or you could do it with a note. And it's saying treat these two 16 millimeter diameters as though they were one feature of size. If I do this, rule number 1 kicks in, which tells me that they must fit through a boundary or envelope of perfect form at 16.02. So both drawings are saying exactly the same thing. You can pick whichever one fits your culture. So, this month's tip to you is tie your interrupted features of size together, especially if they will be serving as your primary datum feature. And I'll see you next month. This month's tip is about a really cool addition to the 2009 standard. Past standards have shown using unit basis control on straightness and flatness. The 2009 revision points out that we can also use unit control on profile. On this part, the 0.6 profile relative to the datum plane established by datum feature A is locating that surface. Now the problem with this is that I might have a very flat surface located near the top of the tolerance zone and then an abrupt change and go down to the bottom of the tolerance zone. So to avoid this abrupt change, I can add profile on a unit basis that we see down here in the lower segment. You can think of this tolerance zone as a coin with a diameter of 10 that has a thickness of 0.1. And this coin applies anywhere, or maybe I should say everywhere, on the surface. So think about it as though you're pushing that coin around on the surface. And no matter where you are, that portion of the surface must fit within the thickness of the coin. So this would avoid any abrupt changes in the surface.
I told you it was really cool. Now, if the surface is a contour, your coin would have to flex to match the basic contour of the surface. We all know rules are meant to be broken. Rule number 1 in the Y14.5 standard is a good example. This rule tells us that the limits of size control the form, straightness, flatness, circularity, and cylindricity of a regular feature of size. Typically, to measure per Rule 1, you make a full form check at the maximum material condition. For instance, for this hole, that would be at its smallest size, or 595, and then local checks to make sure it isn't too big. If it passes these checks, then the feature's form must be within the limits of size. In other words, the form of the feature is dependent on the limits of size. You could always override this rule with a node in the past, but now, as of the 2009 standard, we have a symbol that will do the trick. It is the Independency symbol. On this drawing, the Independency symbol has been applied to the 10 millimeter diameter shaft. This means that the form control of this feature is totally independent of the size limits. If the size limits are met with a measurement that ignores form variation, like this 2-point micrometer measurement, great! But be careful. If the limits of size are not controlling the form, you better make certain something else will. On this drawing, the runout tolerance is not only locating the feature, but it's also controlling the circularity and straightness of the feature. So when do you go for this Independency symbol? Well, my rule is that you should really consider it when the length exceeds 5 times the width or diameter of the feature. This is because Rule 1 may become impractical where a tight size tolerance has been applied. Just one more of the new symbols in the 2009 standard. I'll see you next month. This tip came about after reading a long conversation on the internet. I hope this will help clear up the confusion.
Often when there's only one datum reference on perpendicularity or parallelism, you can end up with an unstable tolerance zone. In this case, I have just datum feature A referenced, which means to inspect the part I would put it against a datum feature simulator, and the part could rock around. This makes it difficult to get reproducible results because the tolerance zone is not stable. I can solve this problem by adding a secondary datum feature, but here's where the confusion comes in. People look at B and say, wait a minute, B is parallel to this surface, it's not perpendicular. And the 1994 standard said, that's okay, B is just there to stabilize the zone. I'd place the part down on the surface plate, and then I would perform my inspection. And as you can see, the tolerance zone is stabilized, and I'll get reproducible results. Now, this entire situation can be avoided if we use the alternative practice found in the 2009 standard. Perpendicularity and parallelism are just special cases of angularity. So in the revised standard, the 2009, we're told that we can use angularity even when we mean perpendicularity or parallelism. So now this should make the confusion go away.
Thanks for watching. I'll see you next month. Years ago, there was no difference between concentricity and runout. They had the same definition. Over the years, this has changed. However, you can still use runout measurement to verify concentricity.
Whether you're doing a circular or total runout check, you're using a single point indicator, and you rotate the part and look at the full indicator movement, which used to be called total indicator reading. Concentricity now is defined as the variation that we have in the derived median points. Well, to derive those median points, you need opposed indicator readings to find those median points. And the tolerance zone isn't on the surface like it is with runout, it's in the middle. So if I look at a runout inspection where I have a single point indicator and compare it to concentricity, as I rotate the part and see the indicator movement, the center or derived median point has moved down an amount equal to the amount of the circular or total runout. So in this first case, I have a feature that is perfectly cylindrical, so all I am seeing with my indicator is the concentricity error. This feature is perfectly concentric, but it's not very round or cylindrical. So all of the reading I'm seeing is form error, circularity or cylindricity. So when we do a runout check, whether it's circular or total, and you can check other tips to see what that difference is, you're really seeing a combination of form error and concentricity. Add them together roughly and you get your runout. Now, for people that pick pepper out of fly poop, this isn't always exactly correct because you may have like a 3-lobed Gleichstick where there would be a slight difference in the readings. But for those of us working in the real world, this is pretty good. The concentricity error must be less than or equal to the measured total runout. So, if the total runout measurement does not exceed the specified concentricity tolerance, the part is good. No need to double the measurement or divide by 2. But why not just forget about concentricity and use runout? It's easier to verify and also controls the form. My philosophy, when in doubt, use runout. I'll see you next tip. I think I could do a tip on composite tolerancing every month. I received 2 composite questions just this past week. One of the questions was, what's the difference between having an orientation tolerance as a second segment of a position control and using composite position? Well, we have this rule that says you're tightening up the location of the features within the pattern if you use composite. Let's take a look at these 2 drawings. The only difference is that one uses composite position and the other has a parallelism as a second segment. An animation will help explain the difference. Let's first take a look at the effect a parallelism has when applied to this position tolerance on the 2 holes. Position, of course, locates the holes relative to the datum reference frame. The parallelism tolerance zones then can float within the position tolerances. So that means that they float independently because it's just an orientation tolerance. It doesn't locate them in any way. However, if we change this to a composite position, this lower segment is called the feature relating tolerance zone framework. That means it controls the location between the features, this 26 basic that we have. It does not control the location back to the datum reference frame. That's the job of the upper segment. That is the pattern locating tolerance zone. So this 20 basic doesn't apply when we're talking about the lower segment. The tolerance zone of 0.2 then can float as long as they float together. So, orientation tolerances do not locate. What part of orientation don't you understand? The lower segment of the composite position tolerance, though, not only orients the pattern, but it also controls the features for location within the pattern. That's a rule of composite tolerancing. Remember, when you're tolerancing a part, GD&T rules, like my shirt says. Right on. I'll see you next month.